Welcome to EPG Pathshala. Today's module is on presentation of environmental concentrations. In this module, I will try to explain how the concentrations are expressed. Environment has thousands of compounds, trace compounds, their concentrations are very small. And for such small concentrations can be as low as 1 into 10 to the power minus 9. So, representation of such concentrations, we use different kinds of symbols and units. The objectives are to define exponents, symbols based on SI units, to define molarity and molarity, to define number density and mixing ratios, to define parts per unit, notations by volume, part per notation by mass, introduction, exponents, environmental concentration units, molarity, number density, mixing ratio, parts per notation by volume, ppm, B, ppv, B, ppt, V, parts per notation by mass by volume unit for trace gases in air, microgram per meter cube, microgram per meter cube. Concentration from microgram to ppb, mass by volume unit for aqueous media, milligram per liter or ppm. Concentration from one unit, conversion from one unit to another, pressure, partial pressure units, and then thereafter suggested readings. A large number of chemical species are found in the environment. To express their concentration, it is necessary to specify the unit of measurement. In general, SI units are used, although some other units may be found occasionally in the literature. SI unit for length is meter, for mass is kilogram, and for time is second. These basic units are utilized to obtain derived units for physical parameters. It must be pointed out that environmental chemistry is concerned mainly with air and aquatic chemistry, and therefore the discussion on units is concerned mainly with these systems. A very important point is first the exponents. What is exponent? Mathematically, exponent is the number of times a number is multiplied itself. Okay? So, this for example, 2 is multiplied to itself by 4 times, 2 into 2 into 2 into 2, it becomes 2 to the power 4. Then 2 is called the base and 4 is called the exponent. So, exponent is the power of the number. Let us see. For the sake of brevity, ease in writing, and to avoid writing several zeros, the exponents as given in table are used. One may come across the units of billion, million, etc. Hence, following quantities, equalities may be remembered. Tera is trillion, giga is billion, mega is million, kilo is thousand, hecto is 100, deca is 10. Environmental chemistry deals mainly with trace amounts of contaminants and pollutants in air and aqueous medium. Therefore, the entire discussion is based on this. This is the table. In this table, the values are given. 10 to the power 12 is tera. Symbol is T, capital T. 10 to the power 9 is giga. The symbol is G. 10 to the power 6 is mega. The symbol is M. 10 to the power 3 is kilo. The symbol is small k. 10 to the power 2 is hecto. Small h. 10 deca da. 10 to the power minus 1 deci d. Now the smaller units on this sides. 10 to the power minus 2 is centi. 10 to the power minus 3 is milli. 10 to the power minus 6 is micro. The symbol is mu. 10 to the power 9 is nano. The symbol is nan. N. 10 to the power minus 12 is pico. The symbol is P. 10 to the power minus 15 is femto. Symbol is F. And 10 to the power minus 18 is atto A. Normally, in environmental chemistry, we use symbols up to this point only. Environmental concentration, the concentration of gaseous substances can be expressed using two kinds of scales, absolute and relative scales. An example of the former are this absolute, molarity, number density, and the latter are, that is relative scales, are mixing ratios and mole fractions. Now first I explain the molarity. The unit is mole per liter. The most preferred unit of expressing concentration of substances in chemistry is molarity. It is defined as the number of moles of a solute dissolved in 1 liter of the solution. Its unit is mole per liter or mole liter inverse. It is defined by equation 1, this equation. Molarity is equal to mass of the solute in gram divided molecular weight of the solute into volume of the solution in liter. That is very important. In many examples, in numerical problems, the volume of the solution may be given in milliliter. You have to convert into liter before applying this formula. Now there is a problem. 100 milliliter solution was prepared by dissolving so much gram of NaCl. The molecular weight is this in water. Calculate molarity. Now how do we calculate it? Molarity of NaCl equal to mass divided by molecular weight into volume in milliliter. This volume in milliliter has to be converted into liter. This is 0.1 liter. So this, if you calculate it, you will get 0.1 liter inverse as molarity. Molality. In this case, instead of volume, we use solvent kilogram. It is defined as the number of moles of solute dissolved in 1 kilogram of the solvent. Therefore, the unit is mole upon kilogram as in equation 2. This one. Molarity equal to mass of solute in gram divided by molecular weight into mass of solvent in kilogram. It doesn't depend upon temperature. Remember this, the molarity may depend upon temperature because it has volume. The volume of the solution may change with temperature. This must be remembered. Another problem. For preparing 0.01 m molar solution of NaCl, how many gram of NaCl should be dissolved in 500 gram of water? Remember, this is the molarity has to be calculated. So, to 0.01, this is the molarity that is. So, molarity equal to mass of NaCl in gram divided by molecular weight into molecular weight of the solvent in kilogram. Remember, this is 500 gram. Convert it to kilogram, it is 0.5 kilogram. So, if you use this, you can get this answer. Remember, the point is the conversion of gram into kilogram is very important. Number density. The number density N is defined by the number of molecules per unit volume. This as in equation 1 equal to number of molecules of X divided by total volume of air. That is the number density, where N is the number density of the gaseous substance X. The unit of number density is molecule per centimeter cube or molecule cm minus 3. Number density is widely used in measuring reaction rates and optical properties of atmosphere. I may point out here, in chemistry, the rates are measured in unit of liter, mole inverse, second inverse. Mole per liter per second, reaction rate, mole per liter per second. Here, instead of moles, it is the molecules which are used. And instead of volume in liter, it is cm minus q. Remember, the concentrations in environmental chemistry are very small. Therefore, this unit is preferred. The number of CO2 molecules in 410 to the power liter air is this, but this is given. Calculate the number density. How will you calculate it? That is, the formula is the total number of molecules of CO2 divided by total number of air. This is given here. This divided by this 5 into 10 to the power 11 molecules cm per cm cube. Mixing ratio. The mixing ratio is equal to the number of moles per mole of air. Number of moles per mole of air, the unit is mole per mole. So, mixing ratio, total number of moles of X divided by total number of moles of air. The mixing ratio is a dimensionless quantity because remember, this is number of moles and this is also number of moles, so the unit will cancel out. So, it will be a dimensionless quantity having no unit. The environmental science in general deals with trace amounts of pollutants in gas phase and with trace impurities in aqueous solution. It is therefore preferred to express the concentrations of trace substances in the form of parts per notation, which can be expressed by volume or mass by mass. You can calculate the mass of a substance, presented how much mass of the other thing, or volume, presented how much total volume of the system. These units are ppm, ppb or ppt are calculated volume per volume or ratio or expressed as, remember, when it is volume ratio, then ppmv is written. ppv, V is written, ppt is written. Normally what happens, in the literature people don't write V and people assume that it is ppm, but correct presentation is it must be written as ppmv. M it is ratio of mass, then it must be written as ppmm. In an environment of the amount COV 1 ppmv, it means that 1 milliliter CO is present in 1 million milliliter of air. M is for billion, this M. Parts per billion, 1 million is 10 lakhs. Parts per notation by volume. The concentration of gaseous substances in air determined as volume by volume ratio should be expressed in parts per billion. Volume, ppmb, parts per billion, B, ppmb, parts per trillion, pptv. Unfortunately, most often B is dropped and values are written as ppm, ppb and ppt, and sometimes this leads to confusion. Now, explanation of this ppme, ppnt. 1 ppm means 1 unit volume of a trace substance is present in 1 million volume. For example, if air reported COV 2 ppm, it means 2 milliliter CO is present in 1 million milliliter of air, or 2 ml CO is present in 1 meter cube of air. ppb, ppb are similar meaning. The amounts of components are expressed in several units which are all proportional to one another. For example, number of moles of a gaseous constituent are proportional to volume. Remember, for a gas equation is PV equal to nRT. Okay? N is the number of moles. If the pressure is constant, then V is proportional to N. At a constant pressure and temperature, this will be valid. Number of moles of a gaseous constituent are proportional to the number of moles. Number of moles of a gaseous constituent are proportional to the partial pressure. You got PV equal to nRT. So P is proportional to N also. So these must be understood and remembered. These are the similarly the other units ppmb. Likewise, the equation for these can be written for others also. Mixing ratio are independent of pressure and temperature. 10 molecules of NO2 are found in 100 million molecules of air. What is the concentration of NO2 in ppb? Now this is a numerical problem. NO2 in ppmb, this here. Number of molecules of NO2. How much it is given? 10. In how much volume? 100. This is 100. Now we substitute this whole and you get this answer. Parts per notation, mass by mass. The concentration of gaseous components can be expressed in mass by mass or weight by weight. Remember, mass and weight in chemistry earlier used to be molecular weight or atomic weight. Now they have been dispensed with. The correct nomenclature is molar mass or atomic mass. But in literature, molecular weight and atomic weight both are used. For example, parts per billion mass by mass, ppmm. Remember, this point must be remembered that here earlier we wrote ppmb because volume was unit. Here mass is unit. It's defined as, or it is also explained, sometimes in some books you will find instead of mass you will find W, that is weight, one and the same thing. ppmm equal to mass of a constituent divided by total mass of the moles of the, all the constituents into 10 to the power 6. Remember, for ppm it is 10 to the power 6. This can be written similarly. Now, there is a problem. 5.2 nanogram ammonia is present in 1.0 mole of air. Calculate the amount of ammonia in ppmm. Assume molecular weight of air to be 28.9 gram per mole. Solution. How will we solve it? In ppm equal to mass of ammonia into 10 to the power 6 divided by total mass of 1 mole of air. Remember, it is present in 1 mole of air, so that's why it is 1 mole of air. What is the mass of ammonia? It is 5.2 nanogram. 5.2 nanogram into 10 to the power 6 upon 28.9. Nanogram is 10 to the power minus 9. So 3.2 10 to the power minus into 10 to the power. This comes like this. Okay? 10 to the power 9 10 to the power 6 upon 28.9 is come to 1.107 into this. Mass by volume unit for trace gases in air, microgram per meter cube or microgram per meter. This is frequently used unit. This is very popular unit in atmospheric chemistry. In air, pollutants are found in small amounts only. And a frequently used unit is to express such low concentrations is microgram per meter cube. Volume of air depends on temperature, while pressure remains almost unchanged. Remember, in atmosphere the pressure is almost 1 atmosphere. So there is hardly any change in pressure, so we can always assume that pressure remains constant. The volume of air depends upon the temperature changes. It is necessary to mention environmental conditions by reporting values in microgram per meter cube. Now, this is a problem. In an air analysis experiment, NO2 was found to be this of air. Calculate the concentration of in microgram per meter cube. Remember, in concentration in microgram per meter, mass of NO2 in microgram, divided by volume of air in meter cube. Since 1 into 10 to the power minus 6 gram is equal to 1.0 microgram and 1 liter is equal to 10 to the power minus 3 meter cube. So using these units we can come out this answer. 1 into 10 to 3 microgram per meter cube. Conversion from microgram per meter cube to ppmv. Sometimes it is necessary to convert. Actually what happens in literature, you have different data on the NO2 concentrations worldwide. Some people have reported on 1 unit, some people have second unit, some people have third unit. How to compare them? You have to use the conversions from one unit to another to bring them in the same unit. That's why this kind of conversions are necessary. Convert, for example, convert 32.05 microgram per meter cube SO2 present in air into ppm at 10 atmosphere pressure 27 degrees. This has to be converted. Okay? SO2 in moles equal to mass divided by molecular weight. This. And convert this into number of SO2 molecules. How will you convert number of molecules? By multiplying Avogadro number. Moles into Avogadro's number, this is the number of moles. Next, convert 1 meter cube of air in the number of moles using ideal gas equation, PV equal to nRT. This conversion is slightly involved. Number of moles of air equal to PV over RT, pressure per atmospheric pressure, volume is this, and this is R, 0.02 in atmosphere unit, and this is the temperature 300 Kelvin. We get this. So if we carry out the calculations, we can get this answer. Convert values of air into number of molecules of air, the similar kind of thing. Mass by volume unit for aqueous media. Now this is also a very popular unit for in water pollution. Microgram per liter or ppm. ppm in aqueous solutions is equal to milligram per liter. Okay? In aqueous system, ppm is preferred and widely unit for representing concentrations of contaminants. In environmental ecosystems, the concentrations of contaminants are generally in the solutions treated as dilute. This is important. So the solutions are treated as dilutes, therefore, density of solution can be taken as 1, that is density of water. In dilute solution, concentration of dissolved solute is so small that density of dilute solution can be taken as density of pure water. Thus, the density of dilute solution will be taken as same as the density of pure water. Let there be x gram of contaminant 1 million gram of solution. By definition, 1 ppm equal to 1 part of the solute presented 1 million part of the water as this equation. So, contaminant in ppm equal to a gram, million gram of dilute solution of water. As discussed earlier, the volume of 1 million gram of water solution is equal to this 1 million milliliter of water, because the density of 1 milliliter is mass of 1 milliliter of water is equal to 1 gram, so they can be interchangeably used. Contaminant in ppm, x gram of the solute divided by 1 million liter of dilute solution of water, x divided by 10 to the power 6. Since 1 gram is equal to 1000 milligram, so this milligram and 1 million liter equal to this we get this answer. In aqueous chemistry, ppm means microgram per liter. So the dissolved amounts of solid, liquids or gases in water are expressed in this unit, which is invariably expressed as ppm. For example, 6.7 ppm O2 in water means 6.7 milligram O2 is dissolved in 1 liter of water. Remember, this dissolution of water is very important, whether river or sea water or lake water or pond water. Now there is a problem. 1 into 10 power minus 4 gram copper was determined in 1 liter of water. Calculate the concentration of copper in ppm and in millimole per liter. What we will do? In ppm, copper in milligram divided by volume in liter, that is ppm. 1000 milligram equal to 1 gram. So many grams equal to how many milligram multiplied by 1000, 0.1 milligram. So we get This copper ppm equal to 0.0 milligram by 1 liter, that is 0.1 ppm. Conversion of from one unit to another. This one. Now, these are the formula. These formulas to be remembered. These formulae are to be remembered because they use the gas equation. Remember here, they are based on the gas equation. So they have to be remembered for conversion. They are easily available on internet or in standard textbooks. Now the partial pressure. Now this partial pressure used in Henry's law and elsewhere. Partial pressure Pi of a constant is related to the total pressure by this equation. What is that equation? Partial pressure equal to Pi into mole fraction of that I constant into total pressure. And how the mole fraction is calculated? The number of moles of the contaminant or substance divided by number of moles of all the other substances N1, N2, this etc. And total pressure equal to the sum of the partial pressure of individual constituents. For example, in atmosphere, the total pressure is 1 atmosphere. This must be the sum of the partial pressure of nitrogen, partial pressure of oxygen, partial pressure of carbon dioxide, partial pressure of helium, partial pressure of argon, and trace gases. Okay? And these are the units of pressure. Atmosphere pressure is expressed several units. This, and maybe 1 or 2 units may be there. So in this module on environmental concentrations units, you have learnt how the concentrations of trace constituents, for example, SO2, NO2, CO, hydrocarbons, etc. can be expressed, and the units are ppm, ppb, ppt. For example, ppm means 1 part in 1 million parts. That is very small constraint, 1 into 10 to the power minus 6. For example, 1 milliliter is present in 10 to the power minus 10 to the power 6 liter, that is ppm. Likewise, other units. Similarly, these units can be expressed as microgram per liter. For metallurgy, the units are of mixing ratios. Because concentration of one species relative to the concentration of all other species, that is mixing ratios. So there are also some conversion units have been given, several examples have been given. If you read them carefully, you can understand the subject. Thank you.